So we have epoxies. Prefix is just epoxy. First example we have here, 1, 2, 3, 4. It's a cyclo. So really this could be 1 for cyclo. Cyclobutane. Then we have one right here. And the general rule with epoxies, you start naming on the two away from the epoxy, the ones that make the connection. So it'd be 1, 2, 3, 4, 5, 5 pentane, 1, 2 epoxy. So epoxy is pretty simple. Here we have just a very simple one, epoxy hexane. And if I were to start numbering this, I would either go 1, 2, 3, 4, 5, or I could go again 1, 2, 3, 4, 5. Keep in mind this is three-dimensional, so it can twist and turn. As these 1 and 2s are also interchangeable. So moving on. Halides. These are one of the simplest types of branches that can come off an R group or a carbon chain. Contains any of the halogens. The ending or suffix to indicate the carbon chain is the root of the element of the halogen ending and an O. Just real quick examples. Chloro, bromo, fluoro, etc. So you get the idea. Here I've got a couple different shapes. We will start right here and start labeling these, and the rule of thumb here is we're going to start with our most complex branch and then work our way around. So this is going to go 1, 2, 3, 4, 5, 6. It's a ring, so it's cyclohex, and then they're all single bonds, so it's just going to be hexane. And we have at the 1 we have dimethyl, and here's where, so this right here, this is dimethyl. Here we have bromo, and here we have chloro. And you would think, just looking at this, you figure, oh, D, that's going to come second behind, well, actually the way it works out is alright, but di isn't really taken into account. It's really this methyl is what we would start with if we were looking for actual naming this. So as it is, this is going to be 2 bromo, 4 chloro, and then 1 dimethyl cyclohexane, since there's all single bonds. Alright, now we have this branch right here, and we're going to start labeling with our longest carbon chain. So that would be 1, 2, 3, 4, 5, 6, 7. Yep, so that's our longest carbon chain here. And what we have here, we're going to start here, and so it's 1, 2. So our bromo is at our 2. So this right here we have 2 bromo so far, 3, 4, and 4 we have a branch that's coming off, so this is 1, 2, 3. Again, our old buddy iso, since it forms that Y shape, isopropyl, since we do have 3, and then 4, 5, 6, 7. So our root is going to be heptane. So we've got our 3 different parts of the word, our 3 different parts of our nomenclature naming here. So we'll just put all together, and I'll just write this up here in green up at the top. Run out of space. So we're looking for alphabetical order. 2 bromo, then at 4, we have our 4 isopropyl, and then our root, which is heptane. So moving on. Ketones, very similar to aldehydes in the fact that they both contain a carbon double bonded to an oxygen right here. The main difference is aldehyde has to contain a hydrogen and a ketone doesn't. So these ketones are actually seen more often in organic chemistry in our in your long molecules than aldehydes, since these have to contain this hydrogen here, and ketones, they can be any number of R groups, and these R's just represent longer carbon chains that could just be attached to them. So some ketone naming. We have methyl butyl ketone. So let's go from this and we will figure out how to draw this. So as it would have it, these ketones are very similar to the ethers when we say there's two different ways of naming this. This right here is the same molecule. These two right here. This you usually see, this is the IU-PAC naming, and this is used a lot of the time when we start getting into some of the longer molecules. But this is probably this is what we call the common naming. And so we have methyl butyl ketone. So what this is saying is we have a methyl, which is just one, and then this is attached to our over here on the other side we have a butyl. So that is 1, 2, 3, 4, and in the middle we have our carbon right here, and this is attached to oxygen. So here there's our 1, this is 2, 3, 4, 5, and we can easily see how this is a pentatone. So it's at our 1, 2, our 2 carbon, and it would be 1, 2, 3, 4, 5. So you can see how that lends itself to be written in that way right there. So let's take a look what happens when we have a cyclo. So we have, let's see here. So again, longest carbon chain, we have 1, 2, 3, 4, 5, 6. So we have again our cyclo. And since with this we have our ketone right here, this is going to be our 1. This is where we're going to start it at. This changes the ending to -one. This indicates that it's a ketone. And I actually just realized when I did my numbering, I did it backwards. This should be your 2. This should be 3. 4 still stay the same. 5 and 6. Because we want to go in this direction because that's where our next branch is. So if we're looking at naming this entire thing right here, we have 1, 2, 3, 4. So 2-chloro is going to be up front. And then we just put our 4, and I'm going to run out of room here. This isn't going to look pretty, but we'll just put this here. This right here, and I'm not sure if I've mentioned this yet or not, this is what we call a tert. And it contains 1, 2, 3, 4. And 4, as we know, is bute. So this is a tert butyl. So I'll just read the name off since it doesn't look so good. This molecule right here would be named a 2-chloro 4-tert-butyl cyclohexanone. Hexanone. Alright, so moving on. Thiols. Thiols are similar to alcohols except the oxygen is placed by a sulfur. It is necessary to add thiol to indicate the carbon chain contains this functional group. So this is very basic. Here's your R group and contains your sulfur. So here we go. 3-butyl 4-dimethyl 2 pentathiol. So this looks something like. Alright, so we're looking at this one. So we have a pentene, so that is 1, 2, 3, 4, 5. And at a 3 we have a butyl group, so 1, 2, 3. So 1, 2, 3, 4. 4 we have a dimethyl, 1, 2, 3, 4. 2. And at 2 we have a double bond. As well as our SH. So that right there is the name for that molecule. And here, looking at this, moving on to this next molecule, this is kind of a clash. Here we have our thiol over here, and we have our alcohol over here. And now, as we'll learn later in our list of precedents, this alcohol is actually going to take priority over this. So what we're going to have here is a 1, 2, 3, and so this is going to be a 3, and when it's a lower priority, the prefix we use is sulfony. And this is a 3, so it's going to be propanol, since our alcohol takes the head naming. So, list of priorities when naming, highest, lowest. First we have our carboxyl, then we have our esters, amides, nitrils, aldehydes, ketones, alcohol, stiols, amines. As you can see, this should actually be ethers, and then our peroxides at the end, which we really didn't talk about. Chair versus boat, equal and exquil hydrogens. Alright, so first of all we have axials straight up and down. That's symbolized by all our reds right here. Kind of a mess, but they're all there. And then we have our equials are parallel to the other bonds. So as you can see here, some of this isn't drawn the best. This should actually be, this right here is parallel to this one. This one right here is parallel to this one here parallel to this, so on and so forth. So you can see that's the key there. They're parallel to other bonds, and this gives it kind of a chair shape. And this is kind of hard to do on a two-dimensional plane, but when you go to build them with molecules in our chemistry set, they're much easier to understand. And the other type of a cyclohexene bond we have here is what we call a boat. And as you can see, it kind of has this boat shape. And what this is, and I didn't label my equals blue on this one, but again, axials are my ones straight up and down, as you can see here, here, and the equals are still parallel. This one's kind of parallel over here, parallel to this, but they're not so much, and they're not keeping those 100 and ideally these want to be at 109.5 degrees. That's what these hydrogens like to be spaced out apart at. And in this one's not so much. This one is much more, this is stable. This one right here is more stable, so we see this one more often than our boat shape. Finally, we have chiral. When a molecule is not superimposable, it is considered chiral. And let's see here. Alright, so I came back and I wrote in some stuff. Here, chiral molecules are not superimposable. They're kind of like a mirror image you have here. Here's my fluorine on top, my bromine. If I were to take a look like a mirror here, I have my two bromines in the middle, and there's no way you can flip this to make this land right on. These molecules will never be the same no matter how you rotate them. And here I have, right here in the center, I have what is called my chiral center, which is usually a carbon atom. And that pretty much wraps